Hello, this is lecture 20 of EP1. In this lecture, we will be talking about fluids. So let me start by explaining what we mean by fluids, even though all of us have intuition about what fluids are from everyday experience, by reminding you how fluids are different from solid objects. So what we did in the very beginning, when we started studying motion, is that we looked at point-like objects. We had these point-like objects. They were moving in space. And at each point in time, you could describe where they were by a set of coordinates, x, y, and z. And then there was a trajectory that described the motion of the particle. And if you have a truly point-like particle, then the only thing that this particle can do is it can move translationally in space. Then we looked at more complicated cases where we had extended objects. So we had extended objects like this. And these extended objects could move, of course, translationally, but since they had shape, they could also do perform more complicated motions. So when we're talking about these extended objects, we kind of made an assumption that they were rigid bodies, and being a rigid body means that they didn't change their shape or their size. So they couldn't suddenly shrink or become bigger, but they could, in addition to moving, they could also rotate around a axis. And the motion of a rigid body in general was some combination of translational motion and rotational motion, and it was more complicated than a motion of a point particle. Now fluids are even more complicated because what they do is when they move, let's use this word movement, they don't necessarily have to preserve their shape. So we have liquids, for example, like water. And if you have water, then water preserves its volume. So it's very, very difficult to compress water and to make it occupy less volume. But it's possible to change its shape. So for example, if you take this glass of water and if you pour it into a vessel with a completely different shape, water will preserve its volume, but it's not going to preserve its shape. And then we have gases like atmosphere. And the thing with the gases is that they preserve neither their shape or volume. You can compress them, you can expand them, and you can change their shape at will. So because of this, because the shape isn't conserved and the volume isn't conserved, the motion of fluids and gases is understandably more complicated than the motion of rigid bodies. So when, for example, water flows and or when you have a glass of water and when you pour more water into it, there are lots of complicated things that are happening during this process. They are kind of difficult to describe. And all of this is happening because this water doesn't have to move as a whole. Each small part of this liquid water, can move on its own. In physics, we call liquids and gases collectively as fluids. And in this week, our main object of study will be fluids, how to describe their properties and how they move under external influence. So I'm now on slide number 3, and what I want to do is I want to start with simple things. Let's say I have a fluid. How do I describe its properties? So if I have this chunk of fluid, and if I act on it with a force, what are good ways of describing the action and the state of the fluid. So when we had rigid bodies, if this was just a box, then we described the influence of external objects with the concept of force, and we described the property of this box with mass. And so mass was telling us how inertial this box is, so how easy is it to move this box under the influence of external objects. And the force was describing the intensity of the action from external objects. Now, thing with the fluids is that if I have a fluid here, and if I apply a force, F, then this fluid is not going to move as a whole, right? So most likely what will happen if I poke this liquid is that the parts that are here will move away, and there will be some complicated motion. And because of this, in many cases, it's more convenient, instead of mass, to describe properties of the fluid with density. So density, usually denoted by Greek letter rho, is mass divided by volume. And instead of force, it's often more convenient to describe the influence of external objects on the fluid with the concept of pressure. So pressure, usually denoted by lowercase letter p, is force divided by the area over which this force acts. So both of these concepts, I'm sure, are familiar to you from high school. We will have a couple of exercises in homework just to remind you how the density and the pressure work. But kind of the physical meaning is that this is mass per unit volume, and this is force per unit area. So if I have a liquid or a gas in a container, then I know that this liquid or gas is under the hood. It's made of tiny molecules that are moving around. And as these molecules move around, they will be interacting with the walls of this container. There will be bouncing of the wall, like so. And as they bounce off the walls, they will exert a certain pressure on the walls. So there will be some force, and this force will be determined by the average collision rate of molecules with the wall, and by the average velocity of those collided molecules. So there is pressure, which is generated by random motion of molecules inside this fluid. If you have fluids near Earth's surface, so let's say this is Earth, and I have a fluid, a really tall glass, and I have some fluid in it, and this fluid is made of molecules, then things change slightly. What changes here is that every single molecule now not only just randomly bounces around, but it also experiences gravitational attraction from Earth. So every molecule feels a force, this external force. And since molecules feel this external force, as they move higher, they kind of lose energy. They become slower. And as they move down towards Earth's surface, again, because of the conservation of energy, they become faster. And so the overall effect of this is that in cases where this distance is not negligible, molecules up here will exert less pressure on the walls than molecules down here. So I hope this is kind of not objectionable on purely intuitive grounds. Because of the gravity, you are colliding more intensely with the walls down here and less intensely on the walls up here. So pressure that fluid exerts on its surroundings when near Earth's surface increases with the depth. There will be more pressure here, less pressure here, less pressure here, so on and so forth. And a very good example of this is actually the atmosphere. We all know that Earth has atmosphere, and the atmosphere is made mostly of, well, it's a mixture of several gases. So the atmosphere, most of the atmosphere is within 10 miles of Earth's surface. And since atmosphere is made of different molecules that move around, of course, this atmosphere exerts pressure on everything. And 10 miles is quite a lot of distance, quite a big difference in terms of energies of colliding and moving molecules. So the pressure at the sea level is significantly higher than pressure at, say, 5 miles above sea level. Okay, so the first thing that we want to do is that we want to find out exactly how this pressure versus depth relationship works. We know that with more depth, you get more pressure. So I will just give you an intuitive explanation of this, and the more rigorous proof is in the textbook. So let's say I have, for simplicity, let's say I have this rectangular vessel, and I have some liquid in it. So first of all, the pressure must depend on how strong your gravity is, right? If I move this glass into outer space, then in outer space, there is no difference really between up and down. So this boundary is the same as this boundary. There is basically no difference. So this relationship, how pressure depends on the depth, must also depend on gravity. So there must be a G here. It then also must depend on the height. It must depend on the H. So the deeper you go, the more pressure you get. And it must also depend on the density of this liquid. Because if you have a denser liquid that weighs more, then if you think about it, let's take this point, for example, you have pressure on this point because of the cumulative effect of this imaginary column of liquid above it, pushing on it. And if this column of liquid weighs more, then you will have more pressure. So the pressure must be also, it must grow with the density of the fluid. And so turns out this relationship is actually linear, so it looks exactly like this. If you have 2 points, this is point A, let's say this is level A, and this is level 2, slightly deeper, then the difference in pressure between level 1 and level 2, which is P2 minus P1, and I will call it delta P. This difference in pressure is equal to the density of the fluid times G times H, where H is the difference in height. So this is one of our key formulas. I will circle it, and I will keep it here for future reference. Now, this formula itself is not very objectionable. I hope it kind of makes sense. But an interesting thing about this formula is that the only thing that the pressure difference depends on is H. And that's kind of surprising because, for example, if you look at, I have a few pictures on my slide number 4. If you had, from this formula, it follows that if you have a vessel that looks like this, and a vessel that looks like this, and the vessel that looks like maybe this, where I have some base, and on top I have some very, very narrow tube. So this is very narrow. Then the difference in pressure, the way pressure goes from here to here, turns out doesn't really depend on the shape of this vessel. So if this is vessel A, vessel B, and vessel C, and if you have the same amount of, sorry, not the same amount, but the same kind of fluid in all three, then pressure down here at the bottom will be the same for all of these vessels, vessel A, vessel B, and vessel C. And that's slightly counterintuitive because you feel like since there is more water here, somehow our intuition tells us that there should be more pressure here. And since you have very little water here, you feel like there has to be less pressure here. But turns out that's not the case. The pressure is the same, the shape doesn't really matter. The only thing that matters is how much liquid, how much fluid do you have above you horizontally. And there are many explanations of this. And kind of one explanation is that when you have a vessel that looks like this, you have kind of this column of water, and then you have this extra water on the sides. But the weight of this, this section is then supported by this extra horizontal wall that we just created by enlarging our vessel to the left and to the right. So anyway, the shape doesn't matter. The only thing that matters is the height, h. So one of the consequences of this is that if you have two connected tubes, so let's say I have one tube, and I have a second tube, and let's say those tubes are really different in size. So this is a narrow tube, and this is a wider tube. If I start putting water, then if I put some water here, then this water will of course flow to the other side, and it will continue flowing until we have the same pressure on both sides. And so the consequence of this formula, our key formula, is that when you are at the equilibrium, if this is the same volume, then it doesn't matter what shape these two tubes have. At the equilibrium, the level of liquid in both has to be the same. So this is the equilibrium. Now, if you have different liquids, so for example, you could be in a situation where you have two tubes connected. For simplicity, I will draw them to be of the same size. So let's say I have this U-shaped tube with two openings. Again, they are connected, so if I put something in here and if I put something in here, they will reach the equilibrium when pressures on both sides are equal. I know that if I put the same liquid, then this liquid will reach the same level. But if I put a lighter liquid, for example, on this size, so let this yellow liquid be oil and let the blue liquid be water, then my condition for equilibrium is that pressures on both sides are equal. And for pressures on both sides to be equal, now I don't really need these levels to be, these two to be at the same level. Water has higher density than oil, and density is important. Your pressure also depends on density. So a good way to think about the situation is to draw an imaginary line, horizontal line here. And then you have an equilibrium when the pressure created by this much oil is equal to the pressure created by this much water. So since pressure is rho times G times H, then if this is H1 and if this is H2, we will have an equilibrium if pressures are equal. So we will have an equilibrium when rho1 times G times H1 is equal to rho 2 times G times H2. So G cancels out on both sides. And if water has higher density, then to achieve equilibrium, you must have oil at a higher level here compared to water. Now let's move to slide number 5. On slide number 5, I have a question. So there are 4 connected tubes that look like this. And there are 4 different scenarios. You have a gray liquid and the red liquid. And the claim is that those are in equilibrium. I'm not going to draw all of them. They are on the slide. And the question is that there is one picture out of 4 that doesn't make sense. There is one picture that's not possible. No matter what kind of liquids you have, there is one case there that cannot really be. And I want you to think about this, and I want you to identify the case that doesn't really correspond to a possible reality. And once you eliminate that case, I want you to look at the remaining 3 cases, and I want to think about, in each case, how does the density of red liquid compare to the density of the gray liquid? So why don't you pause here, think about this, and then come back. Okay, so the first question was, which situation is not a possible situation for the equilibrium? And the answer to this question is that it's case number 2, because in case number 2, you have something like this. You have this red liquid, and then you have this gray liquid. And from the picture, it looks like the gray liquid on both sides is at the same level, okay? And this means that the pressure on this side, only accounting for the gray liquid, is equal to the pressure on that side. Now, if you add more of red liquid, the pressure will increase. So there has to be something here to counterbalance that pressure. And since there is nothing here, this is not a possibility because there is no way that you could have this situation and have pressures equal to on both sides. You must have something here, some amount of gray liquid to make pressures equal. So B is not a possibility for a static equilibrium of 2 liquids in a tube. Now, if you look at cases 1, 3, and 4, which are possible cases, in case number 1, you have a situation like this, where if you look at it carefully, I will draw horizontal lines here. If you draw a horizontal line where the red liquid starts, you have kind of more of the red liquid in terms of height compared to the gray liquid. And since the pressures must be equal, and since the pressure below this line is equal, because you have the same liquid, the conclusion from here is that the red liquid must have a lower density, because it takes more of the H for this red liquid to balance the gray liquid. So for case A, density of red must be less than density of gray. I'm not gonna go through cases C and D. I will leave it to you. Think about how do the densities of gray and red liquids compare in those 2 cases. And if you have any questions, please let me know during my Zoom help hours on Wednesday and Friday, 12:30 to 2:30. Okay, so this is the end of the first half of lecture 20. In the second half, we'll talk about buoyancy and what happens when we submerge objects into fluids.